Well, if you came here trying to learn about spectroscopy, and all I did was show you a bunch of examples of a time-independent field interacting with molecules, you might say, what's the deal with that? I have a laser, I have an NMR spectrometer, I have something that is time-dependent, the field itself. Let's do something with that. All right, one of the things that you are going to want to expect to see is something like resonance. So let's see if we can figure out where that comes from. Now, linear absorption and linear interaction with light is probably the most common way that most people will do spectroscopy of one sort or another. So we will consider that. So remember what we have. We have the series. We have the time the time evolution operator for the H0 part of the Hamiltonian. Think of that, if you want, as the molecule. Then we have the light, the field that's going to be on, and we know how that shows up. That's going to be the last little bit, H primed of tau, not tau n, there's only one tau in this case. Then we have the first little bit before we get to tau. Okay, so we worked out what to do with this, right? Because we worked out a little bit, what we saw with the time-independent case. With the time-independent case, we wanted to work out the transition probability, go from ground state to first excited state, or any two states, let's say. And we realized that we needed to evolve the state of the system with this time evolution operator. And then we take the modulus squared. So that's sort of a similar thing that we're going to do here. We're just going to add in a tiny bit more about what H primed is. Instead of it being a constant, we're going to make it be an electric dipole interaction. So an electric dipole interaction can be written down relatively straightforwardly like this. So it's going to be an operator, which we'll call V, okay, times an oscillating frequency, cosine omega t. All right, now what is V? V will be minus mu, oops, there's no minus sign, minus mu dot E. So this would be like a field. That would be like, that's like the cosine part. We're going to just extract this a little bit and make it minus mu, the magnitude, times the magnitude of the field. So basically what we're saying is, let's make this simple for ourselves and have our field aligned along the dipole moment of the molecule. So we know that the scalar product is as big as it can be. And then we're only looking at that component of the field. Okay, so this becomes a pretty straightforward perturbation or expression for the perturbation Hamiltonian. The mu is going to have the operator part in it. Right? If we do an actual calculation, this is going to have a field strength, and this has where the frequency of the field will come in. Right? What we're interested in is the probability of going from J to K, as we've done many times, which we know how to do as a scalar product of our time evolved state vector with whatever state it is that we're interested in. This is going to be starting in the ground state. So we'll have this. The first order time evolution operator is here, the initial state is here, and the thing that we want to check with is over there. Okay, so far so good. Now, if we just make our lives a little simpler and assume that we're not going to go from the first state we start into the same state we're in, then we'll assume that J is not equal to K. That gets rid of this term. And all that we have left is this bit here. All right, so we have already worked out some aspects of this, right? We worked out this term basically in the general case before we had any specific perturbation that we were putting in, and then we put a few examples in like a constant, whatever. All right, so what we're going to do is we're going to make use of what we've already worked out. And remember how this worked. These two U's, these two U0 terms end up having like things that depend on T and T0, right? And things that depend on tau. And you take the T and T0 part out of the integral because it doesn't depend on tau, and then leave the bit in that has tau that's left over. And then the idea is to remember that bit with the t and the tau ended up being just a phase. The phase goes away when you take the modulus squared, right? So we're going to do that. The way I'm going to do it to save a bit of time is we're going to work out the term without the mod squared. Well, we'll just leave the mod squared written there. All right, so we have minus I over h bar. And then what we're going to do is we're going to take the part, I'm just going to call it f of t and tau, t naught, sorry. Right, this is the piece that's like the e with the terms. It's like ej minus ek tau, and then the other one is e. Well, I won't bother repeating it. Okay, so then the rest of it is the interesting part. That's the integral d tau, right? Which was, if we remember, just equal to h prime, all right, kj tau, that matrix element, times this exponential e to the I omega of kj of tau, this thing squared. Okay, and the thing to remember just that this f, when you mod square it, is going to become equal to 1 when you modulus square it is equal to 1. Okay, so we're going to take a look at this h prime kj. And h prime kj we know is going to be a number, right? This magnitude minus mu the magnitude times e naught the magnitude, which we'll just call that v, times cosine omega t. We do need, I shouldn't say just the magnitude. This is not the magnitude. This is the operator here. Okay, so we're going to work that out. I'm just going to leave that in as a transition dipole matrix element that you would need to calculate for whatever spectroscopic condition you are looking at. Okay, so what that's going to leave us with then is what we're interested in is looking at this integral part. Right? So the integral part will be minus I over h bar. We're going to leave out the f because we don't care about the integral part. We don't care about the not integral part. All right, and then we have h prime kj. So that's going to be the kj element of this. All right, so it's going to be v kj times cosine omega tau, because it depends on tau, e to the I omega kj tau. Okay, and so the way we do this now is we break up the cosine, and there's probably 100 different ways of doing this. The way I'm doing it is I'm going to break up the cosine into exponentials, and then we're going to distribute the product with this. Okay, so cosine, recall, is equal to 1/2 times e to the I omega tau, cosine omega tau, plus e to the minus I omega tau. It's the sum of the sort of forward spinning one and the backward spinning one, and it gives you a standing wave. That's a cosine. Okay, so we plug that in to this integral bit, right? So we have minus I over h bar, a tau. We have this magnitude that we will probably leave unworked out because it's going to depend on the problem that we're interested in, whereas the other conclusions will be very general. Then we write down the exponentials, so e the I omega tau plus e to the minus I omega tau. And then we have e to the I omega kj tau. Remember, omega kj is not a parameter, right? I mean, it's not a variable. This is a parameter. This is telling us about energy level spacings between the levels that we have, right? If this is energy k and this is energy j, then omega kj is just equal to ek minus ej divided by h bar. Right. That's fixed by like Mother Nature. This omega is something from our light source. We can tune it. Now, of course, what you expect is that as you tune it to be equal to omega kj, then the effect will be very big. And you tune it away, the effect will be very small. All right, so let's see how that actually works out. So first, to do some simplifications of notation, we will set t naught equals 0. That just gets rid of this lower limit, right? And then we're going to make one other not simplification. We're just going to expand this out, which I'll write down here. So that's minus I over h bar, t naught to t d tau dkj, and then we have these two exponentials, right? E to the I omega plus omega kj tau plus e to the minus I omega minus kj tau. The sign here is always positive, so if we put a minus sign, we have to have a plus. Now, remember this vkj is not a function of time anymore, so it can come out of the integral, an integral between 0 and t d tau of these two different terms. And I'm just going to write them down here. Okay, so we can write down what this integral is. You can either look it up, you can do it in Mathematica, there's lots of different ways. All right, so it's 1 minus e to the minus I, and then the order, of course, of all this stuff is important, omega minus omega kj t, and then it's all divided by omega minus omega kj. All right, the other term is similar, of course, we're just changing around the signs. There's something missing here, there's a tau missing. All right, so we have e now to the I omega plus omega kj tau, and that is equal to the similar formula, e to the I omega plus omega kj t divided by omega plus omega kj. Okay, so this gives us two terms that we're going to add together, multiply by minus I v kj divided by h bar, and then try to simplify as much as we can. Right, so we put the pieces together, and we get the integral part, right? Not the part before that's going to go away, and not the mod squared. So we get minus I v kj, which is now just this constant that we have to calculate. We have a factor of 2, 1/2 for the putting it into cosine, and then we have h bar that was already there from before. We did the integrals, we wrote them all out, and so they are minus I, and then we have e to the I omega plus omega kj of t minus 1, just changing how we're factoring things, divided by omega plus omega kj, the frequency gap, minus I times 1 minus e to the minus I omega minus omega kj t divided by omega minus omega kj. In the previous thing, we had this switched around in order, the order was different, but these are all, equivalent to each other, of course. All right, good. So then now what we do is we take out that factor of I, right? So we're going to have I times all this stuff. So that's going to get rid of the i's and give us just a minus sign. So I times I will be minus 1. There's already a minus sign there. Take out these minus signs then. And we'll take the minus sign out to the front. All right, so that gives us minus, overall minus vkj over 2h bar. And then all we're doing is just rewriting this. There might be a more convenient way to write this. E to the I omega kj plus omega. It's this positive sign, so it makes no difference. Minus 1 divided by omega kj. We can swap order if we swap the order here. So we have e to the, and then we can swap the order inside here. So we have e to the I omega kj plus or minus omega t minus 1 divided by omega kj minus omega. So now what we do is we make use of the trigonometric identity that I showed you earlier on, which is to recognize that this thing here is like e to the I theta minus 1, And this is also like e to the I, a different theta minus 1. Those can be replaced with the term that had the exponential and the term that had the sign. Right, so in this, to go from here to here, we use the trig identity. Theta minus 1 is 2i e to the I theta over 2 sine theta over 2. Okay, so let's do that. So we get minus I, oh right, so the I is coming from here. VKJ, but I thought I got rid of the I's over here, but they come back. Yay. The 2 cancels this 2, right? And then we have the very interesting terms that are coming now. So e to the I omega kj plus omega times t divided by 2 times the sine. And the sine bit is going to have omega kj minus omega times t over 2 divided by the same thing, omega kj plus omega. That's term 1. Now term 2, e to the I omega kj minus omega t over 2. Then we have our sine, omega kj minus omega t over 2, and its denominator, so it doesn't change. All right, so we look at these formulas. Now, of course, to get the actual transition probability, we need to take this whole thing and do the modulus squared. Okay, and so what we want to do is we want to think about this. Remember what the omega is. The omega is coming from our light, or our field, whatever, probably light or spectroscopy. And the omega kj is coming from the molecule or the material. It's the energy gap, frequency gap between two levels. So generally speaking, of course, there are ways, if you imagine, manipulating molecule or atom atomic properties with yet more fields, you could potentially change this. But let's take this as sort of given to us from Mother Nature. But omega is something we can adjust. Maybe we have a laser, maybe we have a light source, a white light source, or some other source of frequency that we can change. Okay, and let's think about these two factors here. You know that when you divide by a number that's very small, that you're going to get a large signal, right? A large thing, a large amplitude. Okay, so what we're asking is when this term is basically 0, right? When this term is 0, then what we have is that omega is equal to minus omega kj. If this is the case, the first term will be very, very large, right? So obviously it would go in principle to infinity. In practice, that doesn't really happen. You'll see this part will keep it from going to infinity like it usually does. All right, down on the bottom, what's the difference here? The difference is we want this thing to be 0. But when this thing is 0, that would be omega is equal to omega kj. Right, so when the laser is equal to omega kj. Now here's the thing. We have not specified k or j yet, have we? We just said they're two different states. So what does the sign of omega mean? The sign of the omega is telling us whether the first state, the initial state, is lower or higher than the final state, right? Let's call this j and call this k. In this case, of course, the energy of the k state is higher than the energy of the j state. So omega kj would mean that we're going from j to k, and we're going up in energy. And omega kj, this number, is greater than 0, and we have the term going up. If, on the other hand, we're going from omega kj, but omega kj, and we're always going from j to k. But j could be higher than k. We never said that they had to be ordered like this. So if they go this way, well then what's this? In this particular case, omega kj is less than 0. It's negative. This energy level is lower than this one. right? So what you basically have are two terms that correspond essentially to absorption and emission, or stimulated emission, or stimulated absorption, and stimulated emission. They both require the field to be tuned to have the same frequency as the energy gap. And that's what's going to make these two terms very large, or get maximized, let's say. All right, so we have our two things. Now, what can we do to simplify this a little bit? One way to simplify this is to pretend like we know what we're going to do in a real experiment. In a real experiment, let's say the system starts in the ground state, and we go to an excited state. So we would go upwards in energy. Right? Then what we can do is we can actually work out what J to K will be. So we know we're only going uphill in energy. Then we want this to be small. That means this has to be negative. So this term here, the upper term, is negative omega kj. So this is the stimulated emission. And this lower one here is the absorption. Right, so we're going to go uphill in energy. So that means this term is the one that's going to dominate. If we compute the modulus squared of this, what will we have? We will obviously get rid of the I business. So we will have V kj squared divided by h bar squared. In the denominator, we will have omega kj minus omega squared. This is not looking really good. This is over here. I'm just running out of board. And then we only have this one term. When we do the mod squared, this field, this phase part will go away, and we'll be left with sine squared 1/2 for this half here, omega kj minus omega times t. All right, so if you compare this to the case where we had a constant perturbation, it should look very similar, right? We had this sine squared dependence, we had the v squared up here, h bar squared on the bottom. But now what we have is this resonance condition. Right? And it just naturally arises from first order perturbation theory, as an example. Now, this is not spectroscopy yet. It sort of is, right? Because you can say, well, it tells me that I have resonance, but it doesn't tell me why I see a signal. It doesn't tell me why I see a absorption or a decrease in transmission when I send light through the material that I'm resonant with. That we're going to have to develop the optical response functions. Right? But it does at least get us to start thinking about how we can think about perturbation theory as being able to describe transitions between states. Obviously, we presume that the field strength, which is all included inside of here, is pretty weak, so that we can use perturbation theory, which is the only thing that we're going to be able to do when it's not possible, for example, to express our system in a basis and solve the Schrodinger equation, which is not generally going to be possible. And also, we want to try to generate generalities. We want general things that we can understand that don't need to be resolved every single time we do a problem. So that's one of the advantages of using perturbation theory, is we can get generic results that we can use over and over again. All right, so that sort of sums up our examples of how to use time-dependent perturbation theory for a few examples. And next is what we're going to do is we're going to get into how to compute these optical response functions. And that's going to take a long time, because we need to first develop a new space for quantum mechanics called Liouville space. And using Liouville space will allow us, a relatively easier way to arrive at calculating the optical response functions. And I say nonlinear because even though the vast majority of people will use linear spectroscopy, it's becoming more common to use nonlinear methods. And also, you might as well learn nonlinear because it's just a generalization of linear spectroscopy.